All right, these problems are doozies, but they're great in that they combine kind of everything we've covered with thermochemistry. And so there's a lot to them. And a lot of them will look similar to this. You might have some that include Hess's law, where you're trying to use that to solve for these problems. In this problem, we have some spherical balloons, radius of 250 centimeters, inflated with hot air and released. And so we need to heat those up. Now they're at 25 degrees and we got to heat them to 100 to make them float. So we're looking at a heat curve here, 25 to 100. We're not doing any sort of melting or change in state because we're already in the gas state. We're just going to heat. So that is Q equals M times specific heat times delta T. So our delta T would be 75 degrees. Now we're also given our specific heat, 1.009. But the hard part of this part, and there's multiple parts to this, is solving for that mass. Okay, so we have a radius given of each balloon. Now you can see the density. We're going to solve for mass from the density. It's in meters cubed, so I'm going to convert centimeters to meters. So I get 2.5 meter radius. Now I got to know the volume of a sphere, which is 4/3 pi r cubed. You should have a cube there, right? The square would be some sort of area, like surface area. So I'm going to put that 2.5 in there, 2.5 cubed times 4/3 pi, and I get 65.45 meters cubed. Now I'm going to take that 65.45 meters cubed, times it by 0.946 kilograms per meter cubed, and then I'm going to go 1 kilogram is 1,000 grams because we have grams up here. So I'm going to multiply that through, and I get 61,916 grams per balloon. So I can solve for my Q now. Right, Q equals 61,916. I'll keep all my digits for now. 1.009 joules. Now this is grams per gram degrees C times 75. Now this is the heat required for each balloon. And I get a huge number here, 4,068 joules, which I can simplify to kilojoules. I'm going to call it 4,685 kilojoules. Okay, I'm going to keep that. I'm going to clear this up, 4,685. Keep that up here, 4,685 kilojoules per balloon. Okay, now that's not all, right? So now I have to heat these with propane. I have 2 kilograms of propane. So I'm going to have to figure out how many moles that is. But first I got to write my balanced reaction. So I have C3H. It's combustion. All these are combustion. So they're going to be reacting with O2. It's going to form CO2 and water. So let's balance this. We need a 3 in front of the carbon. We need a 4 here. And we get 4 plus 6, 10. So we don't need to double everything. Oh. Don't want to erase here. We want to draw. There we go. So there's our balanced chemical equation. Now we need to find what the enthalpy of the reaction is. How many kilojoules per mole of propane do we get? Then we can apply that to this kilojoules per balloon. Now you could probably just look it up. What it's telling you here is the enthalpy of formation of just propane. Now remember, enthalpy of the reaction is the sum of the products minus the sum of the reactants. So I have to look these all up. Now you can look them up here in data. I started doing it, but this is in the thermodynamic properties of pure substances. Oops. So I could Where'd it go? There we go. And you can do control find and see H2O. Now remember, there's liquid and gas. Make sure you get the gas one. So I'm looking at this column right here, 241.8. Now, so let's clear this. I have these. So the enthalpy of the reaction would be equal to the products. Now remember, you got to multiply it by its moles. So I'm going to say 3 moles CO2. Now CO2 is negative 393.5 kilojoules per mole. I'm going to add that to 4 moles of water times negative 241.8. Now that is all minus 1 mole C3H8 times, now I can use this number here, oops, times negative 103.8 plus 5 moles O2, and O2 is 0. So that one's going to go away. So I get 3 times negative 393.5 plus 4 times negative 241.8. And I get negative 2,147.7. And then it's minus a negative 103.8. So I get negative 2,043.9 kilojoules per mole of reaction. Now, how many moles do we have? Well, we have to do, I'm going to go 2,000 grams of CO2. Molar mass, or sorry, C3H8. So 2,000 divided by 44.1, I get 45.35 moles. Now I could times that, kilojoules per 1 mole. Now this is only 1 mole, because there's a 1 in front of here. If there were 2 in front of here, this is that part of the reaction where this is an inequality. What's the enthalpy of reaction per mole? It would be different for O2, CO2, H2O, because those have different numbers in front of them. But if I multiply those two numbers, 45.35 times 2043.9, I get negative 92693. That many kilojoules available. So that's the amount of heat available. So I could make these positive. This is how much it takes per balloon. They're both in kilojoules. So I'm going to do 92,693 available, divided by the 4,685 of each balloon, and I get 19.79 balloons. So how many can I completely fill? I'm going to say 19. There we go. And that's a counted number. So just the 2 digits, not 19.0 or 19.78. It's just how many full balloons can we fill. So ton to this, right? Enthalpy, we're dealing with enthalpy of reaction. So we have a certain amount of propane that can be used to heat. We're looking at heating curves. But in this point, we're just looking at the raised at 75 degrees. And so we're assuming no wasted heat and all that. But kind of a cool question to summarize what we've learned.